Good evening and welcome. I'm Emily Teller, Chair of the Publicity and Outreach Committee of Westford Climate Action, and we are very excited to be here with you tonight as Massachusetts Institute of Technology's Haystack Observatory staff and scientists host and inform this evening's presentation. I'd first like to give you a little background about Westford Climate Action. WCA began less than 2 years ago with just a few residents who were concerned about the climate crisis and believed that Westford residents and government could be doing more to meet the challenge. We began by attending both Energy Committee and Select Board meetings to advocate for a greater percentage of renewable energy in the town's residential and business electric aggregation contract. The renewed 3-year contract, approved by the Select Board in May of 2020, provides these ratepayers with a higher default percentage of New England-only renewable energy sources, now at 30%, and with 2 other options for raising their renewable energy percentages to 50% or 100%. In October of 2020, after collecting over 250 signatures, Westford Climate Action brought a resolution to special town meeting, directing the town to establish a Clean Energy and Sustainability Committee. The resolution requested the new committee be tasked with developing a climate action plan to reach net zero greenhouse gas emissions by 2050. It was passed overwhelmingly. In February of 2021, the Select Board formed the Clean Energy and Sustainability Committee, and work on the town's climate roadmap began. This Clean Energy Committee is in the process of engaging town departments, committees, community organizations, residents, and businesses in fine-tuning the plan on how all can play a role in implementation. Over the past 2 years, we have had guest speakers on energy-related topics and hosted webinars on solar energy and heat pumps, and we plan to offer more like this one. Last week, we hosted the superintendent of schools to discuss his role and vision for our students and staff as relates to sustainability and climate change, and how Westford Climate Action can help. In April, to celebrate Earth Day, we will be partnering with the Fletcher Library, Clean Energy and Sustainability Committee, the League of Women Voters, the Recycling Commission, the Conservation Commission, and the Westford Conservation Trust for a month-long series of events and activities. I would finally like to recognize and thank our other partners in tonight's presentation, the League of Women Voters of Westford and Westford's Clean Energy and Sustainability Committee. We are so grateful that MIT's Haystack Observatory, hold on a second, page down, okay, just a minute. We are so grateful that MIT's Haystack Observatory very generously offered this presentation. Thank you also to Heidi Johnson, who has arranged the technical portion, and John Tsai for his technical support. And thank you to each of you who is here this evening. This webinar is being recorded and will be available on Westford Climate Action's website in the near future. I would like to tell the audience that the usual Zoom chat is not available tonight. You may type your questions anytime during the presentations in the Q&A box, which should show up somewhere on the edges of your screen. Questions will be read and asked of the appropriate speaker after both have finished their presentations. There will not be time for spoken questions since we currently have over 150 attending. I would now like to turn the evening over to Nancy Wolf-Kateri, Haystack Observatory's Communications Director, to introduce our speakers, Dr. Lonsdale and Dr. Ilosity, and moderate tonight's forum.
Hi everyone, I'm Nancy. I am the Communications Officer for Haystack. I would also like to thank my colleagues who made this possible, in addition to Westford Climate Action, did a great job. Heidi, John, and Drew are here to help us make sure everything runs smoothly, so thanks to them. I would also like to introduce 2 of my scientist colleagues tonight. The first is Dr. Colin Lonsdale, a radio astronomer and the director here at MIT Haystack Observatory. Dr. Lonsdale has been with Haystack since 1986 and became its director in 2008. He is also the chair of the Event Horizon Telescope Directing Board. He will introduce Haystack Observatory tonight and explain some of the latest data available on climate change. After Dr. Lonsdale, our second speaker tonight is Dr. Pedro Ilosity, who joined Haystack as a research scientist in 2014 and currently leads the Geodesy group at Haystack. He is also a senior researcher at the Institute of Marine Sciences in Barcelona. Tonight, he will describe some ongoing climate-focused research in the cryosphere. So as Emily stated, we will have questions afterward. Please type them in the box at any time and I will pass them along during the Q&A time. Thanks.
Okay, so I guess I'll start my talk at this point. I'm delighted to be here. Thank you, Emily, and thank you, Nancy, for the introduction. I'm going to share my screen now. Hopefully everybody can see that. So I'm going to, as Nancy said, give an introduction to Haystack Observatory and then go through some of what we currently know about the state of climate change. And then talk a little bit about what we might be able to do about it before handing over to Pedro to talk about some of the climate change related research that's going on at the observatory. So the title of this presentation is Meeting the Climate Challenge, the view from MIT, from an MIT Observatory. And this is indeed a view from an MIT Observatory. What you're looking at is Haystack Observatory. There's a very large radio telescope inside this dome. And there are a number of other instruments across a 1,300-acre campus out in Westford. And we do a lot of different types of research there. We share the site with work being done by Lincoln Laboratory of MIT, but Haystack is a separate unit that does pure scientific research that's unclassified, and we publish in all the open scientific journals, all of our work. So this is an aerial view of the site that we have. This is the access road coming off Route 40, and you can see several of the different installations at the site. Most of the site is just wooded land. And there's various instruments and storage buildings and radars and the big dish at the end, and office spaces and various other things. And this is another view looking the opposite direction. So what do we do at Haystack Observatory? So this is a research center that does a number of different activities, working in a number of different scientific areas. So we do radio astronomy. That's mostly funded by the National Science Foundation. We do geodesy, which is something that Pedro will define and describe in more detail. That work is mostly funded by NASA. We also do geospace science. That is the study of the near-Earth environment, the upper atmosphere and the plasma environment in which the Earth sits. And that part is mostly funded by NSF, but a different part of NSF. And then we also have we're very dedicated to a mission of education and public outreach, of which presentations like this are a part. So we have an emphasis on doing science, mainly through technology innovation. We like to develop new techniques, new instruments, new widgets, and then use those to push science forward. And the thing that ties most of our activities together is that we work with radio waves. We are a radio observatory. This is not all just looking out at the stars and galaxies, but looking at the upper atmosphere and looking at ways that radio techniques can help us understand the world around us. And you might ask, so what does all that have to do with climate change? And it's a perfectly good question. But the answer is that lots of science is interconnected. It's rare that you find a field of science that doesn't touch many other fields of science in some way or another. And radio techniques in particular support a lot of different types of investigation. So you can use radio to do very many different kinds of remote sensing, finding out about things from a distance. Radio is at the basis of precision location finding with GPS. And that same location finding allows you to monitor how various things move, like glaciers and icebergs, which you'll hear about, continents drifting apart, and animals that might have been tagged with radio locators. Communications, of course, are a huge application of radio techniques. We've been using radio waves to study black holes in the deep universe, and that's part of what's been done with the Event Horizon Telescope project that we're a big part of. One of the things that we do is amazingly precise measurements of the orientation of the Earth in space, and looking at just exactly how it spins and wobbles. It's not a nice smooth motion necessarily. So these radio techniques that are employed to do all these things complement and help others do many different areas of science, and that includes climate science. And the climate crisis has been identified as a grand challenge by MIT, and Haystack is committed to engage in that and help in ways that we're particularly qualified to do. And what we want to do, our contribution will primarily consist of contributing to the knowledge and understanding of how climate change is happening and where it's going. So this is just one slide to illustrate that even when we're not deliberately trying to focus on a climate change topic, our basic research touches on it anyway. So this is a slide that describes a technique that we've been doing at Haystack for decades. It's called Incoherent scatter radar. And what it is you fire some really powerful radio waves, basically straight up. And when you get high enough, there's free electrons in the upper atmosphere, and those scatter the radiation, and a little bit of it bounces back into our dishes, and we can detect it. And exactly the way that they bounce back tells you all kinds of interesting things about the physical properties up above our heads, hundreds of kilometers up above our heads. One of the things it tells you is the temperature of that plasma. And so we've been observing throughout the year and throughout the time of day and throughout several decades. This is a map of all of the observations that have been done, and you can see it's completely filled. There's been radar observations done continuously for decades. That's a tremendous database, and it allows you to look at how the temperature in the upper atmosphere might have been changing over those decades. Climate change. It turns out, if you look at this graph over here, that at an altitude of 400 or 500 kilometers above our heads, the temperature has been going down steadily for about 50 years. That is actually an expected consequence of the process of climate change that we hear about all the time. The lower atmosphere is warming, but the upper atmosphere is actually cooling. It's all part of closely connected processes. So we were doing climate change work before it was fashionable. So let me now turn to summarizing what is known about the current state of climate change. And this is best looked at using the periodic reports of the Intergovernmental Panel on Climate Change. And there's a new release of this, the assessment report number 6, that is basically based on 2019-2020 state of affairs, and the publication is coming out in 2021 in pieces and over the next several months. The one piece that's available right now is what's called the Summary for Policymakers on the Physical Science Basis of Climate Change. And I'm going to draw quite a lot from the content of that report. It's very similar in scope to what was done several years ago in 2013, assessment report number 5. But since then, there's been better data, more sophisticated analyses, and the uncertainties, the errors on the estimates have shrunk. So we're more sure about a whole bunch of things regarding the process of climate change. That leads to more refined and more detailed conclusions about what's happening and what's going to happen. So let me just say a couple of quick words about these assessment reports. This is the one that was AR5 in 2013. And if you look at the credentials behind this report, it's really very impressive. This particular report is just one of 3, and it's the one about physical science. It's over 1,500 pages long, and it is impressively peer-reviewed. It's one of the most comprehensively peer-reviewed summary of the state of a scientific field that you'll find anywhere. It's been scrubbed and scrubbed If there's something that's not quite right, then it will have been criticized and changed and scrubbed, and it will have been concluded that we can't really say that, so we better caveat it properly. All of those things have been thoroughly done. 54,000 independent reviewer comments doing that scrubbing. So if you're looking for something that has really been through the ringer to make sure that it's accurate and justified, this is where you look. And now, of course, AR6 is 2021 and not 2013. So the most obvious and basic conclusion is that the Earth is warming, and it's warming very quickly. And here's a couple of graphs to illustrate that not only is it warming quickly, but it's warming because of us. So this graph here shows the last 2,000 years. And this line is a well-established estimate of the temperature with the potential errors on that estimate of temperature over the last 2,000 years. And at the far right, you see what's been happening just in the last few decades. It's anomalous, obviously. This little bar over here is an estimate of how warm it's been on an extended period basis anytime in the last 100,000 years. And we're even above that line. So basically what the story is that it's warmer now than it's been just about in 100,000 years at least. On the right is two sets of curves. The blue one is a simulation based on our best modeling of what the temperature profile would be like if humans had not been around. And the brown one is a modeling of what it would be like given what we know that humans have done to the greenhouse gas environment of the atmosphere. The black line is the observed temperature record. So the observed and simulated look very, very close. And this is one of the main pieces of evidence justifying the conclusion that humans are causing the planet to warm up. So I've here grabbed just a sampling of the statements that you find in this report. And you'll notice as you scan through those that there's various places where it says high confidence or very high confidence in some conclusion or other. So let's just step through a few of those. Up at the top, it says atmospheric CO2 concentrations were higher in 2019 than at any time in the last 2 million years. That's a pretty profound statement. And then other gases, the increases in CO2 and methane, CH4, another potent greenhouse gas, far exceed changes between glacial and interglacial periods over at least the last 800,000 years. It's also, here's another one. Human-induced climate change is already affecting many weather and climate extremes in every region. We can already detect some of the effects that have been predicted in terms of how extreme the weather can get. The signal is there and we already see it. Another one, many changes are irreversible for centuries to millennia. We've already passed the point of no return on many of these changes, particularly the ones affecting the ocean, the ice sheets, and the global sea level. Those things are changing and they're going to keep changing for a long time to come, and there's nothing we can do to reverse those changes. If we want to actually do something significant about this problem, then the conclusion is that if you want to stop the warming at a certain level, you have to reach at least net zero CO2 emissions. Right now, we're emitting 35 gigatons, 35 billion tons of CO2 per year. And we've got to get that to zero if we want to actually get things to stabilize at some point in the future. And then the final one here is a little less depressing. So there are some scenarios that I'll explain these scenarios in a minute for very low levels of greenhouse gas emissions. That if we were able to follow those projections for our emissions, then it wouldn't take very long for us to notice the improvement in the trajectory. The difference in trends of global surface temperature will begin to emerge from the natural variability within around 20 years. That's a pretty short time. It's not like we're locked into things getting worse and worse for a century. We can interrupt this. So here's the bottom line. On balance, this is all really, really bad. And we've already caused significant damage, some of it irreversible. Nevertheless, we still, even at this stage, have the opportunity and we have the technology to start bending the curve pretty soon. So there's plenty to fight for. So here's what they did in this study. They defined 5 different levels of climate action. And it's defined by the way that there are emissions of different kinds caused by human activity. So this one is carbon dioxide. And there's very high levels of emission going out to 2100, medium, medium low, and then very low. In fact, in these last 2, it actually goes negative. So we're taking carbon dioxide out of the atmosphere in these scenarios. And then there's other pollutants, methane there, nitrous oxide, and sulfur dioxide, different scenarios with different predicted consequences. Over on the right, you see the amount of temperature increase by the end of the century that is predicted according to these different scenarios. All of them have significant temperature increases. As you go to the worse and worse or less and less responsible scenarios, then you get to more than 4 degrees Celsius increase in temperature. These are just the different parts of that make up that increase. This is the CO2, this is the methane, and this is actually something that tends to cool the planet a little bit, the sulfur dioxide that is particulates that shade the Earth a little bit, but nowhere near as much as the Earth is heating from the greenhouse gases. So you'd really like to be with one of these 2 things, which is we're at 1 degree Celsius now, or just a little bit more, and you really don't want to go much further for all kinds of reasons. I also threw in here, this is a little bit more esoteric, but as you increase the amount of CO2 that you pump into the atmosphere, the land and the ocean absorbs some of it, but not all of it. And the more you pump in, the smaller the fraction of what you're pumping in can be absorbed by the ocean and the land. So actually what's left over to go into the atmosphere goes up very quickly. So there's a big difference between these in terms of what actually ends up in the atmosphere. Okay, so some of the effects of this, some of these, no doubt, lots of people already know, but extreme weather events become much more common. They're already much more common than they were in the past. So agriculture and ecological droughts are now already nearly twice as common as they were before all this warming started happening. And if we keep at it and go up to those higher levels of 2 or 4 Celsius, it's going to be many more times frequent. The frequency of extreme high temperature events, heat waves, potentially hazardous to health, the increase is more dramatic. We're already experiencing what would have been a once every 10-year event, nearly 3 times more often than we used to. And by the time we get to 2 degrees C, which is going to be very tough to stay below this, it's going to be 5 or 6 times more frequent than it used to be. And if you go to even more extreme events that used to happen only every 50 years, then by the time you get to 2 degrees C, it's 14 times more frequent. So you get one of these things every 2 or 3 years, or 3 or 4 years, when they used to be every 50 years. So these are rather dramatic changes. This leads me to this, this graph, which is one of the more complicated graphs I've got here, but it summarizes things very well. This is an attempt in this report to summarize impacts of this climate change that are of most significance to civilization, to society. And there's a whole bunch of different things: mean surface temperature, extreme heat events that I just talked about, floods, landslides, droughts, fire weather, hurricanes and typhoons, the loss of ice and snow and glaciers, obviously the atmospheric CO2, sea level rise, flooding, associated flooding, ocean acidity, posing problems for shelled marine animals, and so on and so forth. It's a little hard to read this, but they divided the whole planet into 50 some different areas, like Central North America, for example. In each of those 50 odd regions, they asked, okay, is this region subject to landslides? Well, oceans aren't subject to landslides. So there's only some of those regions that are subject to that. So in each region, if the phenomenon is going to become less frequent, it's to the left. It's going to become, if it's going to increase, it's to the right. So for everybody everywhere, the mean surface temperature is going to increase. This big dark bar says that's pretty much a certainty. And similarly, just about everywhere, not quite everywhere, cold spells are going to become less frequent. Now, that's the most basic and simple thing, right? But there are other things in here that really make you take notice. Fire weather is going to go up a lot. This lighter bar means that it's probably going to go up. The solid bar means that it's almost certainly going to go up. This is all for about the year 2050 or so not that far away. The cryosphere that Pedro will talk a lot about, that's all going to shrink with high certainty. The permafrost is going to shrink with high certainty. Lake, river, and sea ice is going to shrink. Atmospheric CO2 is going to continue to go up for sure through at least 2050. The sea level is going to rise. Coastal flooding is going to get a lot worse. Coastal erosion is going to get a lot worse. There's going to be marine heat waves. This is the kind of thing that kills coral reefs. And the ocean acidity is going to continue to go up. Down here in the open ocean, you've got dissolved oxygen. The ocean is not going to be able to hold as much oxygen in the future. So all of these things are pretty well locked in. So it's a rather sobering list. So this is a broad brush summary of how things that society will care about will affect us in the near future. What it doesn't address is how societies are going to react to all of that mayhem. Here's a few more projected changes. It's pretty much all the same story. I'll go through this very quickly. Global surface temperature, it depends what scenario. If we get really aggressive and successful, it holds down to maybe below 2 degrees, but probably not. If you're careless and carry on as we're doing now, it'll go up to more than 4 degrees. Sea ice is going down. If you look at sea volume, it's actually more dramatic than this. Acidification of the ocean. This is the sea level change. And although it's fairly modest so far, just a few tenths of a meter, by the end of the century, some of these scenarios are approaching a meter. And if things go wrong in the Antarctic in particular, or Greenland, then it could be quite a bit more. By the time you're getting several feet of climate change, the impacts become very serious. Right now, you just have to spend a few $1 trillion building seawalls and coping with frequent floods. But as this is a cumulative thing and it's accelerating and it's unstoppable, even the low scenarios, it keeps on rising. If we do it wrong, then you get into this region, which is a projection for the year 2300. And now you're talking many meters, and you see this one says sea level rise greater than 15 meters cannot be ruled out with high emissions. 15 meters is 50 feet. That's catastrophic, utterly catastrophic. And if we lock things in with one of these high emission scenarios, that may well happen. And our descendants will not thank us. So things are only going to get worse unless we bend the curve. Avoiding these high emission scenarios, or even the yellow one here, is an emergency priority for the planet. So what's the industry view of all this? The science is clear. What needs to happen is clear. The consequences if we don't do it are clear and becoming clearer all the time and with every IPCC report. Industry takes a look at demand and supply and the market pressures and where profits can be made and what the industrial community will do and what the demand for energy will be, and it makes projections. So this is kind of a typical representative projection of the energy industry. This is the percentage of total energy generation that is projected to happen beyond the present for coal, for natural gas, and for oil. Those are the fossil fuels. And then the non-fossil sources of energy, nuclear power, hydroelectric power, and renewables of various kinds. So this kind of looks a little bit optimistic in that they're converging, and you can sort of see at some point that maybe renewables will overtake the fossil fuels. But if you look over here, this is the total. This is not the fraction of the total. This is the total. And the fossil fuels are the green, red, and gray bars added together. So over the years, this is the amount of CO2 that is being emitted and then now projected to be emitted, and it just keeps going up. You should compare this to these graphs. So industry is saying, okay, well, business as usual, we're going to go up one of these curves here. And we just saw what the consequences of that are. So here is an analysis by an energy company, BP, which looks at, okay, well, this is a serious business. We better see what it would take to bend these curves down to something a bit more survivable. And so they look at the year 2040 and say, okay, what would we have to do? Well, there's various measures that some people may think would be effective, like banning internal combustion engines and switching all over to electric cars for everybody. Doesn't make much of a difference. Here again, you've got the same colors, and the gray is still way up here. And then by the time you start seeing a decline, these are all for the same time, 2040. What are these categories? It says RE push. A push on renewables. Okay, that helps a bit, but it doesn't get you down below where we are right now. Okay, push harder. And what's it called? Faster transition, whatever that means. And if you really want to, that gets this green curve here that's starting to look a bit more like this. And if you want to go down steeply, which is what SP 1-1.9, great naming convention there, they call it even faster transition. No sense of how on earth you would do that from the industry point of view. The bottom line here is that the current market forces just are not going to do the job. You need either regulation or a transformation of those market forces to make a dent. Let me just say a few words about, I'm going to really speed up here because I'm going too slowly. So this is a couple of slides about why it's like that. This is just one natural gas field. It's got 516 trillion cubic feet of natural gas. It's out in Pennsylvania and West Virginia. And these are all the wells, natural gas wells that are being drilled to tap that. So that's the problem. The fossil fuels are there. They represent huge amounts of money. And because the energy industry knows that if they don't use it, it's going to go obsolete, and that money will never be realized. So there's tremendous pressure to get out and burn it now and get the money. That deposit alone is worth $1 to $2 trillion. And a pipeline that was planned to be built, actually didn't get built yet, would transport $600 billion worth of gas over 50 years. So there's a massive incentive to do that. Once that pipeline is in place, it's almost free to get the gas out. So once it's in place, it's all going to burn. Bad for the planet. So new fossil fuel infrastructure is bad news, and we don't want any. Just a couple of words about climate myths before I move on. There's lots of them. Some people say it's not actually happening. Well, yeah, it is. It's amazing the gyrations they go through to claim that it's not. They say it might be the sun. As an astronomer, I can assure you that it's not. It won't hurt anything. Well, the previous view graphs put the lie to that. This is one that I really like. It's frequently asserted that one volcanic eruption dwarfs human carbon dioxide emission. The truth is that humans do 35 gigatons a year of CO2. Global volcanism in an average year is 0.26, and the biggest volcanic eruption in recent history, Mount Pinatubo here, emitted 0.05 gigatons. Humans are winning this race by a factor of 135. There's alarmism too, and this is a bad thing to propagate. Everybody hears that the coasts are going to be flooded soon, the city is about to drown. You've probably seen pictures like this, New York City being inundated. But it's a fairly slow process, and this isn't going to happen for at least 150 years, this picture. So let's not get too excited about it for the next few years. The Gulf Stream will stop and Europe will freeze. You might remember this movie. Well, the thing that might slow down is the Atlantic meridional overturning circulation that drives the Gulf Stream, and it's slowing down, but it's not going to stop, and Europe isn't going to freeze. And then this one is melting permafrost. Again, it's a relatively slow process, just like the melting of the ice sheets. It takes a long time to melt that much permafrost. So it's happening, methane is being released, but it's relatively slow. So exaggeration is not a good idea. It offers critics who want to get all that oil gas out the ground ammunition to say these guys are talking nonsense. So I'm going to spend about 3 more minutes here wrapping up. So this is a point that I really want to make that is often missed. So people focus on the wrong things about what to be worried about. Should we be worried about warmer winters? Well, especially not right now, we shouldn't be. But no, that's not the thing to worry about. What about devalued beachfront properties? I wish I could afford one. But no, that's not the thing to worry about. Hungry polar bears. There's all kinds of nasty things happening out there, but that's not really what we should be most worried about either. There are changing flood and drought patterns, and this can disrupt agriculture. There's faltering ecosystems and the spread of disease, especially insect-borne diseases. This is happening. There are headwinds for developing economies, more poverty and associated exploitation. And all of those lead to economic and environmental refugees on scales that we've never seen before. That leads to political instability, rising nationalism, persecution, and regional conflict. And those things in turn produce yet more refugees and wider and broader political instability, and that can lead to much more devastating conflicts. And all that can happen long before any cities drown. So this is the thing that keeps me awake at night. And that's not the only chain of consequences that you can imagine. You can pick your poison, an increased frequency of pathogen emergence, which is kind of relevant these days. Crop failures and the economic chaos in the USA. There's real threats of serious drought in bread baskets in the nation's heartland and in California. The collapse of the ocean ecosystem in various ways. The question is, how does human society handle those changes, and can we handle them without conflict? This is the thing that worries me. What's the answer? We know that we have to create an economic incentive to do better. Because of time, and I need to make sure that I don't hog all the time here, I'm going to skip over this. The bottom line is that we're in very deep trouble with the climate. So there's economic things that we can do, like a carbon tax to help set priorities. We can accelerate clean technologies and doing research plus those economic incentives. We're not going to get there without that. There's bad government policy that can lock in burning of fossil fuel reserves, like allowing the construction of major new fossil fuel infrastructure. But public opinion is absolutely central. It can foreclose key options like nuclear. Nuclear doesn't produce carbon dioxide, and it's a much bigger threat than radiation. And it can offset big energy lobbying for permanent infrastructure. So what are we doing to help? This kind of communication, open houses at the observatory, outreach, and venues like this one. We can contribute to the understanding of climate change using our specialized expertise, like this upper atmosphere thing that I mentioned at the beginning. And we can do targeted direct research using our expertise in radio techniques. And that's what Pedro is doing and is pursuing an active polar research program. And it's time for me to hand over the microphone to Pedro to describe all of that. I will stop share at this point.
All right, so do I go next, Colin? You done with that?
Yes, absolutely.
All right, so thank you very much. Thanks for the intro, Colin. Thanks, Emily, and the whole Westford Climate Action Group there. It's fantastic and delightful to be here. I'm gonna share my screen. Hopefully will went fine. And I'm gonna make it. Here, you see it well out there?
Yes.
All right. Probably I'm gonna turn my screen off because I wish you all were here at Haystack, and I like to give it face-to-face seminars or talks instead of being sitting down in front of my computer. So when I do that, I sort of, wave a lot and just move a lot and talk a lot. And that means that if I'm on the screen there, I'm gonna distracting you all. So if you don't mind, I'm just gonna switch it off, and then I'll be standing and walking as I'm talking. I hope that's fine with you. If I can find out the mute and the stop video. All right. So Colin has given actually quite a quantitative approach and understanding of what's the climate situation, climate crisis, and the MIT Climate Initiative for that matter, because it's an understanding by everyone that it's a fundamental problem that we have right now. My approach is going to be, having been his quantitative, mine is going to be qualitative. And therefore, what I'm going to show is a few snapshots of the kind of things that Colin has explained and introduced on the polar north and south, so Arctic and Antarctic. And that's the kind of things, the polar research that we do at Haystack. And I'm going to deal with that with the snapshots of, first is we're doing geodesy. We're doing geodesy out of the polar environment, but we do geodesy in the polar environment as well, in the cryosphere. And I'll come to describe what the cryosphere is in a second. But in a nutshell, we're doing geodesy on glaciers, we're doing geodesy on icebergs, we're doing geodesy on sea ice, we're doing ice sheets and ice shelves. And what I'll do is just move through the kind of projects that we're working on in each one of these, topics in the cryosphere. If this thing works. Can I move to the next slide? There you go. So let me just first say in one word, what is geodesy? Is that still up on the screen fine? Here is not flipping properly, yeah?
Yes.
So geodesy, just in one word. So what you see on the right hand, it looks like something deformed, like a ball. It's actually planet Earth, or it's supposed to be planet Earth. And it's supposed to sketch a representation of, the kind of different forces. On the bottom, you see melting of ice, which is what we're talking about today. Ocean loading, atmospheric pressure, as we know, so like changing continuously with weather. On the left top, you've got winds, and it's the different forces that make the planet, which is broken up in different plates. And you see one crack there that it's like where along the faults where earthquakes typically happen, right? And that's, that's really what Earth is. It's a dynamic system, or planet Earth, a dynamic, it's a rotating, as Colin said, and geodesy, it's really about the science of the Earth's shape, is the science of rotation and the science of gravity. And that is, how Earth is deforming, the evolution over time, how Earth is reforming, how Earth is rotating, how the gravity changes as mass moves from, the polar caps to the oceans and mass is redistributed over the surface. So that's geodesy. And one example of geodesy, what we do is to measure with very good, incredible accuracy or precision. It's any point on the surface of the Earth where we've got a geodetic instrument, and I'll come in a second to that, with a millimeter precision. So we're able to measure if we, trimming our fingernails, and after 3-4 days, they start to grow again, a millimeter. And I'm mentioning that because, the inches and so on, just to make it clear, a millimeter is, the little tip of your finger when you trim your fingernail, the fingernail when you trim there after 3 or 4 days. So it's a little teeny tiny thing. And we do that globally. We're able to measure positions with that, kind of precision. Bringing it home before we get into the widest stuff, which is the polar component of the polar caps. Colin gave a very nice intro of Haystack. I wanted to show this one. So Haystack, for those of you Westford probably recognize this, Haystack, the top of the hill is at the very end. So that's the inverse picture, I think, of what Colin was showing. I'm showing this because on the bottom right, it's Westford. And Westford, which if you were to go inside, and many of you may have done that inside Haystack, and maybe at Westford as well, you would see this radio telescope there, that it's about 18-meter diameter. And I'm showing this is because that's a radio telescope used to look at, stars, quasars, galaxies in an interferometric mode to be able to determine the position of that telescope on the surface of the Earth, in this case, at Westford, with a precision of a millimeter. And this is another view of the same, radome looking west now. And next to it, if you, paid attention on the bottom, there is a GPS receiver. And this is the same GPS receiver you would have in your car, or we have in our car, we have in our mobiles. It's only that instead of using one of the signals of GPS and determining where we are moving and how we're driving and in which road we are, more or less, and which crossings are coming, we can determine with that antenna that is pretty much bigger, much bigger than anything that you can put in your mobile, we can determine where that little point is with a precision of a millimeter again. And that's very important because for anything that we do on the poles, anything that we do anywhere globally, from other geodetic instruments, satellites that do altimetry and look at sea level that Colin was mentioning, they need a reference frame. They need something to tell them where they are relative to something that is fixed on the ground. Well, Westford has two of those instruments, the Westford radio telescope doing VLBI and the Westford GPS antenna doing GPS geodesy. There are two anchor fiducial points of everything that we do globally at the millimeter level on our planet, be that deformation, be that rotation, be that helping physical geodesy, which is the gravity field. So those two things about what is geodesy. Now switching to the polar research. So now we're gonna go from the nice, beautiful green that we saw there to the nice, beautiful white. And Colin mentioned the cryosphere, and the cryosphere in just one word, it's where the world is frozen, where things are white and it's frozen. And our research, what we do at Haystack, it involves projects. We are doing work in collaboration with many other groups, many universities. Colin mentioned the funding. It comes from NSF, it comes from NASA, it comes from other funding agencies as well. We do it in Greenland, we do it in the Arctic Ocean, we do it in Antarctica. We collect data that involves all kind of state-of-the-art or state-of-the-science, if you will, techniques that involve GPS. We don't go with the radio telescopes out there, but GPS, those antennas, and we build the technology to be able to anchor them on icebergs, on sea ice in Antarctica, and we'll come to in a second to that. We use radars, we use lasers, seismic waves, so seismometers. That is not really geodesy, but it's complementary because what we do is the combination of geodesy and geophysics on all those things, glaciers, icebergs, sea ice shelves, to understand what is the response of that world frozen stuff, the cryosphere now, and trying to figure out what are the implications and the predictions into the future climate. So bringing just as a context, 2 or 3 things that I think wrap up nicely with what Colin was presenting before, but in a photo illustrative way. And probably this is the most dramatic example, and Colin mentioned that, of climate change. And this is the huge rapid changes that are happening in the Arctic Ocean. And on the left and the right, I don't remember really the years, but we've been looking at, meaning the whole science community, and has been looking at what is the extent of sea ice in the winter, in summer, and comparing year after year. What you see on the left is that so like bright white, that's thick ice, and that's the ice that has been there for more than a year. The thin grays is the ice that grows, the ocean freezes, and it grows in the winter, and then it stays a little bit in the summer, through the winter into the spring, and then by the end of the summer, it's already melted out. The part that it stays right there, it stays like in the Beaufort Gyre, that is the part north of Canada or north of Greenland, depending on the surface currents in the Arctic. It stays there hopefully for a long time. On the right, and that started with, satellites started to go up there in the 70s. On the right, it's not really the last year. If I show it what it was a year before, 2 years ago, 3 years ago, it'll be much less than that. But that is the reduction of thick. The important thing here is that the thick multi-year old ice in the Arctic is disappearing rapidly. It's actually already disappeared by now at the pretty much, compared to where we were 30 years ago, 90% level. And it's important, this is very important, because the thick ice is the ice that is slow to move, is the ice that stays in the summer, is the ice that reflects the radiation and doesn't let the ocean absorb the heat, and is the ice that is less mobile. As we loosen that, we go in quickly, and we've lost already, as you see there, enormous amount of multi-year ice. That's a implication, critical implication in what's the climate here in Boston and all over the planet. What happens up there, propagates and has an impact everywhere. So that's perhaps the most dramatic example. That's the one that actually in movie fashion, we see that continuously. If we flip to the southern, actually still on the left, so this is using all the geodetic instruments, and that's the ISAT laser altimeter. So that's an altimeter that it was launched in 2004, and this is a satellite launching a laser and just looking at the reflection from the top of the ice sheet, and that's doing pretty much topography. And this is important. There was one mission in 2004. There was just one, the ISAT-2, launched a couple of years ago. And this is the amount of ice sheet mass, the continental big thick ice, 3 kilometers thick, that it's covering Greenland and covering Antarctica, and how over this time, over 15 years, has been lost or is being lost. And the red color, the scale over here, is in meters of ice per year. We're losing from Greenland about a number that I think Colin mentioned before as well, of the order of 250 gigatons of ice per year. And this is 250 cubic kilometers per year. And just to put that in a scale, if we have a 1 kilometer line and 1 kilometer thick, is pretty much the amount of ice from here all the way to New York. That amount of ice we're losing every year to increase atmospheric temperature, we're losing in Greenland. And you see there on the bottom of the scale, that's like purple color is about 10 meters per year. Something equivalent, a little less right now, but something equivalent is happening in Antarctica. And in particular, on the west side of Antarctica, you see that the Amundsen Sea, you may have seen in the news, the Thwaites Glacier, that's the part that is really going right now at the level equivalent of Greenland, close to the 10 meters per year. We are, a factor of 2, maybe less, over the whole entire Antarctica than in Greenland, but it's going at a level that it's equivalent there. So all that, actually, it's important to quantify, and what are the drivers, identify what's happening there. In one case is the atmosphere, in the other case, pretty much in Antarctica, is the ocean. And where is that water going? And that's another graph that it was shown before that I showed here a little bit differently. And this is since the launch of the satellite radar altimeters. And this is the series of Topex Poseidon, Jason 1, Jason 2, Jason 3, that are doing the same as the laser, but here is a radar with a GPS flying there. And since 1993 to where we are right now, it's an increase in global sea level, or is rising right now at the level of 3-something millimeters per year. Over these 30 years, it's been at the level of almost 6, 7, 8 centimeters there. And if you notice the curve there, even though it's not, this is very projected, there is a curvature here. You will notice that in the 90s, the slope was a little bit less than in the years early 2000, and it's a little less in turn than in the where we are right now. That means that the faster we go, there is an acceleration. So there is more water being dumped into the ocean at a higher rate. And that maps into where we'll be in 2050, where we'll be in 2100, and from there on, depending on what happens in Greenland and what happens in, most fundamentally, in Antarctica. So if we're coming back home, and home means here, how do we do cryosphere? And this is just our polar research, where and how we do it. And you can just go clockwise, or you can go counterclockwise. On the top left, there is actually on the top right, so we've been doing, and that's what we'll start with, studying glaciers in Greenland, some of these big, fast-flowing tidewater glaciers. And you see the archetypal of that might be Helheim, that I'll come to show a few things. Up on the northern, glaciers that are also breaking apart, creating icebergs, and we'll follow, pictorically, we'll follow a couple of icebergs down Baffin Bay. And jumping to the top left, we're doing all kinds of GPS and radar and laser and all those things in collaboration with other institutions on the sea ice on the Arctic Ocean, with deployments north of Greenland, ice camps, with deployments, recent one north of Alaska. And the same thing will go, so like we will do a little bit of on Antarctica on the bottom. We use, helicopters to fly over great glaciers and instrument them and study how they deforming and they move in. Up on the top, we use, huskies. I think that's what they call, right? Husky doggies, just to go on the fjords and again, deploy instruments, measure the thickness of the ice, see how they're changing over time. We're working with local indigenous populations there, where they've got the experience of, what is safe and what is not safe. And we sort of bring the technology and working with them just to help them continue doing their life and their work. On the right, you see an icebreaker. That's another way that we go to sea ice. On the bottom right, it's a GPS testing element that we were deploying early on to see if we can actually look at the tides and detect how they're going up and down as the whole sea ice is moving or drifting. And I show in that one because that's kind of like dark color. And dark color is something that looks like seals. And we don't really use any polar bears, but polar bears, are on the hunt all the time. And anything that every time they see something that is smell and something that is dark, they go, hey, I'm curious. Let's see if that GPS receiver happens to be a seal. And we've got all the systems and instruments many times. That's the excuse of the engineers. When they stop working, they say, oh, that was a polar bear. That's all I broke it. But we love to work with them, and we've got them visiting all the time wherever we go in the Arctic. So I'm switching to, gonna go through, as I mentioned, the kind of snapshots of glaciers, a couple of snapshots of icebergs, and then we'll do a little bit of sea ice, and we'll just wrap up there. So glaciers, I mentioned, this is Helheim. That's what a glacier looks like when you're coming in. One of these huge tide water. They call tide water because the tongue of the glacier, which is what we see here, the Calvin front, it's actually tidally going up and down and back and forth with the ocean tide. And this is Helheim, and it goes about a meter per hour or thereabout. And that means that if you're sitting on the side, as we sort of doing, we are on the southeast coast of Greenland here. If you're sitting on the side, as you're doing here, we've got a GPS instrument deployed there on bedrock so that we can jump down with other instruments, and we can just look at the displacement and how displacement changes over time. How is tidally being forced? Are they going to break? How are they thinning? How are they retreating the Calvin front over time? So if you look there, you're sitting there quietly and thinking about it, you say, wow, you hear actually the grind of the glacier going at that sort of meter per hour is pretty significant. You hear nature just flowing there when you're sitting. And this is if you fly now to the top of the glacier, you would see here, it's a big, this is an extension. So it sort of flows gravitationally. It comes from the Greenland ice sheet and flows. By the time it gets to the ocean, it's flowing faster and faster and faster. So it's in extension mode. And you see here how broken it is, how crevassed, and this big crevasse here right before the Calvin front, it sort of shows and it looks at that piece, that sliver of ice is gonna break anytime. And in fact, just for a scale, on the right-hand side here, it's a helicopter flight going over the Calvin front. Just for a scale, this is about, the Calvin front, the part that is floating, it's about 100 meters. That's where you see the helicopter there. What's under, because this is ice floating, it's in total, it's about 1 kilometer. So these things are huge rivers of ice coming down from draining the continental basins. So that's the kind of studies that we do. We jump to the glacier. That's a one GPS system right there on the Calvin front, because we wanted to study one dynamic effect. Is how they flow, how they thin, how they calve, how they break up. And we've been monumenting in particular this one. You see one example here that is like 20, 30 of them that we've been doing over the years. And we've sort of been with other instruments as well, like radar interferometry, for instance. This is a very good place to do work and be away from the polar bears, because it's so broken up and so crevassed that they are smart enough to know we're not gonna get there. You are on your own, deploy your instruments, that's perfectly fine. If we turn that glacier around or that helicopter fly around and we're looking down onto the ocean, this is the kind of things that you see. And you will notice there is a, a number, so like the part close to the Kelvin front, this here on the bottom here, as we turn 180 degrees, it's actually the melange. So that's the parts and pieces that are broken, some of the icebergs, that this one on the left is like something that is clearly has tilted over. This is the wall that was either, probably this is on the back, it's like roll over 90 degrees. And some of them are pretty significant. They go down the fjord, and in this case here, then they make a right, and 100 kilometers later, they hit the ocean, saline water. And so we started looking at how they drift the icebergs when they calved, how they melt once they get into the fjord, where does all this fresh water go, and how that mixes with the continental Greenland, East Greenland continental, currents that come down along the coast, how this fresh water and saline water mix, and what's the effect on currents, depending on, dynamically, the more and more icebergs and more fresh water that we put in there. So this is one example of, we jump carefully on top of some of those icebergs, and we select instrument with some of the GPS receivers that we built here at Haystack. And you'll see here an example of two, prototypes that we built. We put on that. In particular, we already down the big fjord going into the ocean, and we sort of, drift, and we bob up and down with the tides, and we sort of like with the little, for scale, little boat over there, and drones flying over, we sort of get a map of what is the topography. With sonar underwater, we get an understanding of what's the keel. And we sort of, with GPS, looking at the vertical component with that millimeter or few millimeter precision, we see how it's melting, and it's getting lower and lower and lower, meaning closer and closer to the ocean. And with that, we sort of have an understanding of the amount of fresh water and how that then flows out and mixes out. So that's, two of the systems that we deployed in this particular iceberg, drifting down the Sermilik Fjord, that is called that one. This is another iceberg, and this is actually, instead of melting, how do they break up? What are the mechanisms for how do they decay? And this is one glacier that came out in the northern part of Greenland. That's a huge one. They're called Petermann's Glacier. And so that guy calved in somewhere around 2010. It was 200 and, that's when it broke. It was about 250 square kilometers. And I looked up and quickly for a scale, that's about 3-4 times. I think it's 3 times the size of the area of the town of Westford. So those things are pretty significant. It's a kilometer deep and 250 square kilometers. We tracked, we follow, and 2 years later, it went Baffin Bay and hit the eastern side of western side of Baffin Bay in Alaska. And that's when, at this point, it was only half the size of the area of Westford. So, it was 1/8 of what had been in the beginning when it calved. And still, the amount of water there, it's equivalent to about 10 years of fresh water that it'd be used, assuming 6 million people in Massachusetts. Takes 10 years of fresh water for the state of Massachusetts, so the population there. And again, just to study how they break, what's the, the mechanisms, those dots that you see there are GPS receivers that we sort of wanted to look again, how they bob up and how they move, how they tide, how they deform. This is a documentary that is actually filmed with the BBC. They had a series with that. So we had with the BBC ship and the Greenpeace. And when we were on top of it, this piece that you see with a different color on the bottom right actually broke off, and we ran away from there thinking, oh, everything is going to break out. I mean, icebergs are very scary thing. They're very, very risky stuff. And so thanks to that, in part, we actually were able to uncover a mechanism of how icebergs break. And in a nutshell is, and this is on the bottom, is the laser mapping of the top of the glacier, the sonar mapping of the bottom, and a mechanism that we call the footloose. So as the warm water on the top starts to create a wave cat and the top breaks out, and that's what we see here on the part. So that goes in and goes in. There's a hydrostatic pressure, a force that the same way when we try to put a football ball in the water, it wants to come back up. Here is a torque that is pushing this part on the right of the glacier that is hydrostatically not in balance, and it cracks at some distance there, and then boom, the whole thing goes, and that's what we saw like called the or nickname or named the footloose mechanism. That it's something that it happens actually pretty much in many of the icebergs that calve in Antarctica. So that was the so far moving or looking into, and that's the kind of the modeling that we get into and the physics that we get into doing of these observations. So I'll move on to the Arctic now, the Arctic Ocean. And we have here is sea ice. And this is an ice camp in northern Greenland at about very close actually to the North Pole at about 85 degrees north. So 500 kilometers from the North Pole. And here we're interested for the reasons mentioned before. Sea ice is shrinking. Sea ice, in particular, thick ice is shrinking. In the summer is less and less and less. Therefore, is more mobile. There is more energy that is absorbed, less than is reflected. You will notice here, just as 101 on sea ice, the camp is on this part that is all rubbled and is, it's got some topography and some roughness. Whereas on the left, with this line over here, that's a runway actually that we created, and it's with an ice plane. We saw that's where we land for being able to instrument the camp and put the GPS there. So this is an opening of the chunks of the flows of ice that when it's exposed to water, it freezes quickly. Thermodynamically, the ice grows, whereas the thick ice grows dynamically. It's, there is a compression event or, low pressure system. One flows, comes and rams on top of another. And so from something that it's about 1 meter thick, it becomes 2, and it becomes older, it becomes 4 meters thick and 8 meters thick, and that kind of thing. So here we, as we said, just in northern, and just to, this is actually give a sense of what sea ice. We come in from icebergs and glaciers that are about 1 kilometer thick. We come into sea ice, and there's a cross section done by National Geographic of what it really, how delicate this whole sheet of 1,000 more kilometers across the Arctic. It's really a two-dimensional thing, because the thickness of the first year ice, the ice that grows every year in the winter thermodynamically and then disappears, pretty much the state of the Arctic now, of the new Arctic Ocean. It's just about 1 meter. It's only when dynamically one sheet or one flow comes in contact with another and is pushed on top of another that we start to have thick ice that is really the one that used to be, and that the kind of sea ice that we would want to be and would love to be in the Arctic for being a state that is not, a crisis there. That's another view of sea ice later in the summer, and that's in the Alaskan part, in the Beaufort Sea. So coming through the Bering Strait, through Alaska, and entering the Arctic on that side, the Alaskan part. And you see how much meltwater is going on the top. That's meltwater is actually absorbing instead of reflecting the radiation. And that is very quickly, that becomes warmer, and that is like drilling through the whole entire sea ice. Before you know it, all those things have broken up in chunks and pieces, and there it's all destroyed there. Here we've got a little GPS receiver that we deployed and was drifting there for a good 3-4 years. And coming closer to this, see that GPS receiver. So the GPS receiver is on the top there. There is an antenna for communication so that we can remotely get the data. And this is the Korean icebreaker. It's set in collaboration. This is multi-international collaborations. A single institution, a single country cannot do this thing. So this is the huge Around is the name of the icebreaker, which is really fantastic that we've been using, and they've been incredibly generous, helping us out deploying the systems there. And this is a happy person, happy student after deploying the GPS system. I'm done it, I'm warm, I'm in the Arctic, but I'm okay. That's not how it was in the past. And I'm showing this thing because going 100 years ago, this is the equivalent of an icebreaker. It's not really an icebreaker, talking about innovation and technology ingenuity. These are the Norwegians, Amundsen and Nansen, when they were trying to figure out what is the Arctic Ocean doing? The same thing in Antarctica. And so they had these hypotheses that there is a big surface current that goes from the Bering Strait out to the Atlantic, and there's this big Beaufort gyre, and that was based on some wood drifting that they had picked up. And so they were adventurous, and they said, let's build a ship before they've broken, the flows would crash and smash and destroy them. But their naval engineering say, how about if we have a ship that when the flows come together, it just pops up instead of staying, crushed in between. And that's the Fram, meaning forward. And so what they did, they came with the Fram in the Siberian side. So they went around the Barents Sea, They went around and the Kara Sea, they ram into the ice, and for 3 years, without knowing, no GPS, where are we going to end up? They were right there on that ship doing all kinds of scientific measurements. Here they are actually, Nansen, and our GPS of our days is that we said with millimeter precision. Here you've got the sextant, which a good navigator would be able probably to position back then, and especially on sea ice if it's not moving, with about a couple of kilometers precision. So in 100 years, we come from 100 kilometers to a millimeters, for a couple of kilometers. Let's say that is 1 kilometer, from 1 kilometer to a millimeter, and that's 6 orders of magnitude, which is really pretty good. In clothing technology, I guess we've also kind of like improved quite a bit. It's really beautiful just to see these guys doing this stuff 100 years ago. This experiment has been repeated very recently. And what's happened? Instead of taking 3 years to do exactly the same thing, entering from Siberia, drifting through the North Pole, coming out in Svalbard, in the Atlantic, it's taking only a year. So that shows the kind of thin, highly mobile, broken up ice that is right now the ice in the Arctic Ocean. So moving to the Alaska, and maybe I'm going too long. Just give me 5-10 minutes and I'll be finished, if that's okay there. So just still on sea ice, this is an experiment that we did recently, and that's again in the same area, north of Alaska in the Beaufort Sea. And this is what it looks as you're coming in. You might see a little camp there where, we built our instruments, radar, laser, our GPS receivers built at Haystack. This is a backup camp in case, something's go bad, and some things went bad. A few things had to be, leave the camp because a big storm was coming and then come back again. And if everything gets broken out, then there is a safety camp, and there is, there's a runway, there is a backup runway. We always play for safety and being conservative. Those are the GPS system, difference from the ones you saw in the iceberg before. Solar panels with rechargeable batteries. We built 12 of those. And this is up on the ice. That's what they look like with a GPS and an iridium. And what we're really doing is just, again, this is the same scale. That's about 2 kilometers between the camp and the backup camp over here, the primary and the backup runaway. We're really interested. This is a radar image, and you see the dark, like before, is the first year ice that hasn't had the time to drain the salt in it. And that's, flat, nice, slick. That's why you want to have the runways there. The brighter is the same as before. It's, it has a lot of structure that's old, a couple of years, maybe 3 years, maybe 4 years old, thicker ice. And that's where we obviously want to set the camp. What we're interested in is just where are the forces, where is the dynamics that breaks up from the scale of a few hundred meters, the smallest chunk of ice that you can have, the flows over here. You see all the cracks that in seismology or plate tectonics, it'll be the faults that generate earthquakes. These are the earthquakes that we sort of look across, see how these little things break up, they open up and they ram on top of each other. So this is still an ongoing experiment. We've got still some of the systems right there. And I'm going to flip back to Antarctica. And this is something that we haven't done yet, but it's part of these MIT climate grant challenges that Colin mentioned before, in which we are involved. So here, the critical thing is, what's happening with Antarctica? And just to make the difference, so just refer to the two terms. The thing on the top of the continent, the continental ice, the ice that is on land, that is what is referred to the huge, massive ice sheet, one in Greenland, the other one in Antarctica. And you see the big ice sheet east in East Antarctica, and the west will be on this part over here. In between, and it's characteristic of Antarctica, it's full of ice shelves. Those are equivalent to the tidal that I mentioned before. These things are floating on the ocean. They come from the continental down the glaciers into these big tongues of floating ice that are kept in place by the boundary conditions on the sides and are floating up and down and generate huge, tremendous icebergs, what they call tabular icebergs. So this is very important for Greenland, just to determine what's going on, because this whole entire part over here, if it goes and it's warming up, and that's where we're losing most of the ice from Antarctica right now, its sea level would go up by the amounts that Colin mentioned before, all the way to 15 meters, and that's totally devastating. And that depends on what's the rate of a few things there, dynamically and thermodynamically. So coming back, this is very important because of sea level. Sea level is definitely rising. It rises at an accelerated pace. It's accelerated because the melt in Antarctica, it's accelerating as well. And this is the equivalent of some of one of the graphs that Colin was showing. The satellite period, satellite data is actually the red thing over here. We only have a little bit just to extrapolate. And how do we extrapolate is very different for the components of Colin mentioning about socioeconomics, the 10 million people that might be displaced, that might have to immigrate or move because of climate is very different. And for managing, coastal towns, cities, Boston, is very different if the projection is on the low end, that it might be somewhere around, a half a meter, 0.4 meters. The uncertainty is huge because it can go, depending on how pretty much Antarctica goes, it can go all the way to 2 meters, all the way up even to 15 meters, as Colin said. And if you are sitting on a board of making decisions about what kind of dams, levees, protections we're going to do, it's very different to be planning for half a meter than planning for 2 meters, which is really pretty much where is the uncertainty with the models that predict less amount of ice going to the ocean. Again, ice shelves, they float on sea ice. They are risky like icebergs are. Actually, they calve and become icebergs. And therefore, is the kind of place where you don't really want to be there deploying instruments. You want to have a way to go to places that are far away, that they are remote. And it's tricky because this is actually a cross-section to a scale of what one of the shelves that we want to deploy, that it's the one that is facing the Pacific, that is very close to the US-based McMurdo, the Ross Ice Shelf. That's a cross-section of what it is. It's pretty much a 700 kilometer long tongue, ice shelf that is floating and being exposed to huge waves coming from the Pacific. And then it's depending on what's the amount of water under and how the water gets there. There may be what in physics is called a resonance frequency, that as the ice shelf is thinning and the vibrations start being bigger, if it goes into resonance and there is more breakup on the surface and hydrofracturing breaking it, very soon you've got that going. And if you've got that going and breaking up, then that's the one that I'm talking about is this red one on the bottom. That's just for a scale about the size of France. So that's almost 500,000 square kilometers, right? But there is, as I mentioned, there are ice shelves all over Antarctica. And each one of those goes, if this breaks, it doesn't raise sea level because it's floating already on the ice. But that's buttressing, it's stopping, it's not letting the ice that it's on top of the continent, on Antarctica, flowing through the icebergs, huge icebergs there, it doesn't let go down into the ocean, which then would cause the huge sea level rise. Gaining access to understanding whether we're losing our ice shelves or not is totally critical for knowing what the predictions are going to be in terms of half a meter, 2 meters, or something beyond that of sea level rise. Is the continent, the ice on the continent, and in particular, the West Antarctic ice shelf, going to go or not? So what we're proposing within the MIT Climate Grant Challenges, in collaboration with other colleagues there, it's to develop the same thing that we're doing in icebergs, in glaciers, in sea ice. So like looking at what is the flow, what is the drift, what is the deformation, what's the fracture of the ice shelves? Are they going to do that with GPS? But instead of going there, boots on the ground or boots on the ice, we're building this ice penetrator. So where we have a seismometer on the bottom, just to look at the vibrations as it's responding to the forcing from the ocean, a GPS on the top, so that it will looking at the flow and the extension and the response to the tides, with communications and iridium antenna, so that we get the data in real time. And this is all like the sketch of what we have in mind and what we're thinking. We're flying airplanes of opportunity or helicopters from McMurdo or other bases around the Antarctica, and we drop these little penetrators. This is pretty much the, looks like a person. It's about 50, 60, 70, 80 kilograms, and it's about 1.5 meters, less than 2 meters, with a GPS and a seismometer. We open, boom, we embed that into the ice shelves, and then we are actually looking at how they are vibrating. We're looking at how they are drifting, and then we contribute to that that data into models and look at the response of the ice shelves. The data through satellite comes to Haystack, and there we do the processing, and then we work in collaboration with, funded in this case, NSF and our colleagues at MIT as well. And so that pretty much wraps up. I think I bring it back home from, given that we have the radome there, to the radome over here, the one we started with, which is Westford. And with the happiest smile of a fiducial point that we are at Westford. We're very proud of it from the VLBI and the GPS point of view, keeping an eye of what's the reference frame, how do we define it, so that we can, with telescopes like Westford and telescopes that we build in with our colleagues at NASA and at other institutions and globally, and that's what you see on the map here, defining under the International VLBI service that reference frame that helps us determine where are the satellites that are doing altimetry for sea level, where are the satellites that ping down into the top of the surface in ice shelves, glaciers, and everything, and be able to track from space and then from the ground as well. And I think I'll stop over here. I've been already walking, I think I've done pretty much half a kilo. What is my pointer here? Am I back? I think I lost it. And show, 1 second, bear with me for a second. If I move to Zoom, I don't know where is my thing here. There he goes. Thanks for letting me turn my camera off. I've done already 1 kilometer or so walking as I was here in the conference room, as if you all were over here. And I turn it on now and I sit down just for the questions that you may have. Thanks so much for your time and for your attention.
Thank you very much to Colin and Pedro for those talks. I'm going to read one question at a time, and I'm going to pick on one of you for each one of them. I'm going to ask my colleagues to do something that's very difficult for them, which is answer these questions very quickly. And that's because we have a lot of questions. So I'm going to limit you to a couple minutes, even if I have to be very rude. So sorry in advance for trying to keep things moving, but we'd like to get to at least most of the questions. I just want to remind everybody, you can type your question in the Q&A box. It's possible that we might run out of time, or I might skip over your question, especially if you have multiple questions. You're welcome to go to the Haystack website, which I will put up at the end of this, and you can send us any really urgent questions to our general email. That doesn't mean we'll be able to answer them all, but we would like to apologize if we don't get to your question tonight. So I'll start off, Pedro, giving you the first question, and just a brief answer. I think you could speak for a long time on many of these questions. If global warming is totally unchecked, how long would it take for both polar caps to melt? Pedro, you're muted. Can you answer that?
If it goes unchecked, and being unchecked means that the whole entire Greenland goes and the whole entire Antarctica goes, which is very, 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 very unlikely. And that's not in any model that at least shows for 2100 or even 2300. Then if the whole entire goes is somewhere around, I don't know, 70 meters or something like that. That's not in the map until at least I think it's 2300. And how much of those projections we believe all the way out to 2300, we need to take more observations. We need to improve our modeling. We need to apply a smarter, learning physics from the data of what we're collecting out there. We need to incorporate mechanisms into, in particular, Antarctica, mechanisms that are not really in the models right now. So 2100 is not going to happen. 2300 is very unlikely. And probably, Colin, you might have that from the IPCC that you've been looking closely in the language that is there in terms of, known very with high precision, less precision, and the language that IPCC uses.
Okay, next question, Colin. We have had safe nuclear fission power generation for years, and it's getting safer every year, but we are not building the required nuclear fission plants. Why, and what can we do to turn that around?
Well, of course, it's been a very controversial topic when you have 3 Mile Island and Chernobyl and Fukushima. People get very nervous about this, and nuclear waste and radiation have always been very scary things. What is needed to turn it around is for the public in general and governments to realize that carbon dioxide and methane are a whole lot scarier than nuclear waste or the risk of nuclear accidents. You're correct that the risk of a nuclear accident is going down dramatically with newer designs for reactors. All the big accidents happened with reactors designed in the 1960s, and those designs are not all that good in hindsight. But there's a whole new generation of small mobile nuclear fission reactors being developed that are self-contained, and they get shipped off to a central location to get recharged. That's a potential game changer. We need all possible forms of non-carbon dioxide producing energy generation that we can lay our hands on, and nuclear fission should definitely be in the mix.
Okay, here's another question, I think also for you, Colin. In addition to fossil fuel regulation, how would a carbon tax transform the demand and supply for fossil fuel usage? Would a carbon tax be a useful tool that also reduced carbon emissions?
There is broad consensus that it would indeed be a useful tool. When people make decisions based on economics, they think short term. I can get this gas out of the ground very cheaply and it's worth X dollars as energy. So you can make a profit, so you do it. But of course, that ignores the ultimate cost of doing that, like the cost of protecting cities against rising seas, or the cost of funding armies to fight the wars that wouldn't have happened otherwise. So if you look at those costs rationally and estimate them honestly, then each gram of carbon that gets released has a cost associated with it, and you should pay for the consequences of that. The carbon tax to actually correspond to that is very high, and getting the political will to impose it is difficult. But if you could, then yes, the commercial pressures would then be, well, let's not burn that coal, let's not burn that gas, let's build lots of photovoltaics instead because it's cheaper. Even though we could get the gas out of the ground for almost nothing, the tax would make it more expensive. That's what should happen. Will it happen? I don't know. It's a tough sell.
Okay. Here's a question that I will try to answer a little bit. Has there been any effort expended to get presentations such as this one as an agenda item on the boards of directors in our industry? So I'm not sure exactly which industry, but we do not usually speak directly to industry leaders. If somebody here is on a prominent board of directors and would like to put us in touch with them, feel free. But most of our outreach is educating the general public and students of all ages. Maybe that will change as things go on. We would definitely like to help educate everyone, including industry. And we do have some projects actually in the works now where the scientists are making a more formal effort to educate people in industries. Colin, I don't know if you want to expand on
I'd like to just very briefly chip in that providing a scientific perspective on this, and in fact, other important topics of interest, like the pandemic or other things, is something that we at Haystack are keen to be able to do to help in any way that we can with providing good information and helping sound reasoning in many topics. We are enthusiastic about doing it.
Okay. Pedro, here's a question. Why is the air temperature in the Arctic rising faster than other parts of the globe?
That's a very good question, and that's the effect that is called the Arctic amplification. And yeah, it's about a factor of 2, so that it's warmer than anywhere else. I mean, one quick mechanism, obvious feedback mechanism there is that as you remove the ice on the top, what you expose immediately directly, it's the ocean. And then the ocean, the difference in the amount of energy that it's able to absorb, one versus the other, is 95% to nothing percent. So in one case, you're reflecting all the energy back into the atmosphere. In the other case, you are absorbing all the energy back into the ocean. So that's a significant component of the Arctic amplification effect. And changing from white to blue, if you will, or from white to something that is dark, and therefore the amount of energy that you are absorbing there.
I think you answered this question toward the end of your presentation, more detail on the Arctic ice loss, multi-year ice, how many years and how long is it melted by how much? I think that was covered.
Maybe, is this about the Arctic or about the?
Yeah, Arctic ice loss,
Yeah.
multi-year ice, I think.
Yeah, so I think, well, I mean, there are two parts there. One is seasonally, and that means from winter to summer, its sea ice is growing and decreasing, going and decreasing, or freezing and melting. The difference between summer and winter, I mean, in the end of the freeze and the end of the melt season, March, if you will, and September, it's when everything is frozen, and everything freezes still nowadays. It's about 15 million square kilometers. So that's what the Arctic is, Arctic Ocean. At the end of the summer, it's less and less and less because it's more and more and more first year ice. And so it goes down from, say, 15 million square kilometers to something that is a factor of 3 less, somewhere around 5 million square kilometers. But that's only the extension and the seasonal. The critical thing, as I was trying to say, is the multi-year ice. And the multi-year ice, the numbers, I think it's, let me just quickly, I think the numbers, if I were to, I said 90% before, I'm not sure I'm totally right about that. I think I am, but if I go to, I would go, as Colin was pointing, I think rightly, the consensus of the scientific community up to state of the art and understanding, that's the IPCC. And so the IPCC says that relative to, so the Arctic has thinned and shifted to younger ice, this first year ice instead of multi-year ice. And since 1979, so if we say 80 and we are in 2020, in the last 40 years, the ice that is at least 5 years old, the thick ice that is at least 5 years old, and that's the kind of ice that is, in the northern part of Greenland, about 10 meters maybe. In some spots might get to 20, but it's, sheets of ice or floes that go together, has declined with very high confidence from the IPCC by approximately 90%. So we just gone from an Arctic Ocean that it was thick years, multi-year ice pretty much, to an Arctic Ocean that it's empty by the end of the summer, and the change is 90% in that more than 5 years. So that's the change. And that has huge implications, on, the everywhere. I mean, the first one you would think of is the climate, right? And the climate is, with less confidence, I think is the IPCC says medium confidence, about to medium. It says the changes in Arctic sea ice has the potential to influence mid-latitude weather on time scales of weeks to months. And that's what I was mentioning before. Anything that happens there that is critical and dramatic, in terms of weather at least, has the potential to be here in Boston in a matter of weeks or months. And then you can just go into everything else in the whole biodiversity, change of species, everything that you can think
of. Okay. Next question, let's see. Probably for Colin. What impact is development and reduction of ecosystems and vegetation having on the rate of climate change? Are current scenarios taking this, the loss of ecosystem services, into consideration?
So the short answer is yes, they are taken into consideration. There's a huge amount of effort that goes into feedback processes. Pedro mentioned one of those feedback processes, the loss of ice and the change in the reflectivity in the polar regions, amplifying the effect of climate change. So by the same token, changes in vegetation have feedback effects on the climate. So the deforestation of the Amazon is a source of CO2. As it turns out, North America, the United States and Canada is reforesting at a significant rate. And it's a complex mix of things that's going on. But the modelers try to take all of that as much into account as possible. And when you look at a report like the IPCC, if those things are not taken into account or they can't be properly estimated, they're added to the error estimate. So the short answer is yes, these things are taken into account. And the best estimate of the consensus of the scientists looking very closely at all of these things is what you see in the IPCC report.
Thank you. I just want to let everyone know that our end time is around 9 tonight. So we're going to finish up around 9. I'm going to try to get through as many of these as possible, but apologies again if we don't get to everybody's, or if you had a complicated question that I haven't asked yet. I'm sorry, but we have to keep these a little bit short. Thank you, by the way, everyone, for your questions. Pedro, just briefly to follow up on what you talked again in your presentation, but question says, are you folks saying that scientists from Haystack travel the world gathering data with various instruments you deploy? Short answer, yes, but would you like to just say something briefly?
You said it.
We do those, a lot of those, not all of the pictures he showed, but some of them.
Yeah, no, as I mentioned before, everything in science, and it's a collaborative effort. And that applies to the cryosphere. I finished with the map about geodesy, all the different station radio telescopes built by partners. In astronomy is the same thing, right? This kind of research is expensive and it's important. And you don't have a Haystack, we don't have an icebreaker. Right? There's no parked or docked anywhere around here. We don't have all the instruments that, or many of them that I'm talking about, radar interferometers, lasers. Our specialty at Haystack is GPS, or meaning geodesy, and geophysics seismometers. So what we do is, like everything in science and everything in life, you sort of team up with those groups that are specialties. They have the specialty on the part that you need to address the science. And in those icebreakers, you would see biologists, you would see oceanographers, you would see geodesists, you would see, everything and everyone that you can think of. And those things are, you put all these things and resources together for a common good of just studying with as many, once you go there, studying with as many, instruments and microscopes and details and everything that you can think of. Yeah. So, we don't have an icebreaker at Haystack. Maybe Colin will get one sometime.
Not yet. Colin, what is the cost of capturing biomethane for natural gas instead of drilling for more?
The problem with something like that is one of scale. The amount of natural gas that is being used right now is phenomenal. It's just huge. And getting that amount of methane from biological methods is, you'd have to have a level of scale up that's unimaginable. What we really need to do is not use methane as much as possible. It is a fossil fuel. It doesn't produce as much CO2 as burning coal or oil for the same amount of energy, but it still produces a lot. And furthermore, as is now coming to light, and is almost certainly included in the IPCC report, it's clear that the amount of leakage from the use of methane, the methane life cycle in the energy sector is much higher than was initially believed. And methane, of course, is a very potent greenhouse gas, making things significantly worse. So I think the right answer here is first of all, scaling it up at that level is not practical, at least not anytime soon. And we should really be getting away from fuels like methane if we possibly can.
Okay. Pedro, a question about sea level rise. Do the projection scenarios of possible sea level rise take into account the positive feedback loops that could occur as a result of ocean methyl hydrate sublimation and Arctic tundra thaw, both of which could release large quantities of methane into the atmosphere?
Can you answer that one, Colin? I don't really know the answer. Yeah.
Well, I don't know the answer for sure, but again, I'll refer back to faith in the IPCC and the scale and thoroughness of the investigations. So this is one of those feedback effects. Just like the melting of the permafrost. The permafrost is melting. It's melting slowly because there's a lot of it. It's like the time it takes for the ice sheets to melt. But in so doing, there are stores of methane that can be released. The question is how much and how fast. That I believe to be quite a slow process. Certainly methane is a significant contributor. It contributes maybe 20–25% of the projected warming. So it's a really serious issue. Is it a dominant issue? No, I don't think it's a dominant issue. But it's certainly part of the picture, and it's a problem.
Yeah, I'm not just to that, not everything or every physical effect, it's included in the models. And there are things at the smallest scale in particular. And I'm actually thinking going back again to the ice shelves instead of the permafrost. There are known effects that have not been included. And that's one of the reasons for the big uncertainties, right? The marine ice shelf instability, the marine ice cliff instability that will solely contribute one way or another. So in the case of permafrost, depends, I don't really know, but there are many things that will have to be included and will make things more accurate as we move on. And models are models, they are not perfect. And the more we know about nature and the physical processes, the more, or hopefully the better they will be. But all those things, I think it's, is, as you said, is the IPCC would be the place just to look into what's the current understanding of all these effects.
But importantly, as you said, if something is not included and we know that it might have an effect or not have an effect, it's included in the uncertainty estimates.
Okay, so I'm going to skip ahead to a question that says, and I'm going to answer this briefly, anything to say about the polar vortex? I do think that both of our scientist speakers tonight would have something to say about that, but because we have another entire research wing that's made up of geospace scientists, and we have at least one person who studies the polar vortex and related phenomena very closely. We'll save that for another talk. So good question, but we'll have to save that for the next time that we have a public presentation. Okay, let's see. Okay, just briefly, Colin, what's your key point to explain to skeptics that climate change is real? I think that's a useful thing.
Well, the last thing I would do is tell them to do their own research. They're not qualified. Very few people are qualified. The people who are qualified are devoting their entire lives to figuring things out. So you go to peer-reviewed studies as the gold standard to find out what's real and what's not. As far as convincing skeptics, well, some skeptics, you're just not going to get there. I mentioned one case where people would do gymnastics to try and argue that the temperature isn't rising. And if you look back at what was happening 5 years ago, there's a whole fuss about a data set that shows that there'd been no global warming for more than 18 years. And it's based on one graph, based on satellite measurements of mid-level troposphere. And it's a cherry-pick thing. There was a big spike at the beginning. And then, of course, it started rising again right after that, and you didn't hear about it again. So people will believe this until the cows come home. And some people, you're never going to convince them. But the most important thing I would impress on anybody is that this is something that people are studying who are spending their whole lives, really, dedicated, smart people with all the right motives, trying their damnedest to figure out the truth. Listen to them.
If I may add one thing, I would just say that the conversation is actually already past that point, in the sense of it's so clear. It wasn't with the AR, the IPCC before and before and before. We are in the 6th, and that means 30 years later since the first one came up. And it's clear from the physical sciences that we are past the stage of whether it's happening or not happening. That's already set. I think the conversation now is moving into the other two components of the IPCC, which is, as a society, what are the impacts? It's happening, period. What are the impacts? How are we going to adapt? What's the, how are we going to be vulnerable? Things that Colin was mentioning there. And then the last one is that, the IPCC wraps up and closes with how we can, do something. What is the mitigation? So we are already past, is it happening or not? We are in the next phase. It's what are the impacts? How do we mitigate?
Okay. Colin, given our lack of progress in reducing emissions and the power of the fossil fuel industry, would geoengineering be a possibility to control the climate?
That is something that's been discussed a lot, like pumping sulfur dioxide into the atmosphere to provide some shading from the sun, or even putting a great big sunshade into orbit, or various other things. They're very dangerous things that would have to be incredibly well understood before you took the risk of implementing such a thing. That's because the way in which the temperature is controlled by the greenhouse effect and the atmospheric gases is entirely different from the way those kinds of geoengineering ideas would change the temperature. So you might be able to adjust the global temperature, but you would not change many other aspects of what climate change is about. It's not just about temperature. Temperature is just a measure of how big the effect is in all of its facets. It's a nice barometer of how severe the effects have become. But you can't reverse all of those effects. The only way to really reverse all those effects in a comprehensive way and a safe way is to reduce the amount of carbon dioxide. So I think you can't rule it out as an emergency measure, but it is a pretty dangerous thing to attempt, and you better understand things much better than we do now before you even contemplate doing such a thing, in my view.
Okay, Pedro, next question. What are the consequences of the deformation, fracturing, drifting, etc., of glaciers, ice shelves, other than sea level rise?
Well, sea level rise is definitely one unclear. Colin just mentioned temperature. So, and we discussed or mentioned that before as well. Even if you're not dumping any water into the ocean, we were not dumping that, and magically solar would evaporate out. The oceans will be getting warmer just because more radiation is getting into the oceans, and that has huge implications into what kind of life, what kind of ecosystems, what kind of biodiversity one has there. It's all over, everywhere on the spectrum. It's, breaking ice has all kinds of implications.
Okay, there are a couple questions about, let's see, here's one question. With increasing greenhouse gases, Colin, maybe you could answer this briefly, and depleting oxygen levels, will it be harder to breathe eventually?
There's other things going to get us long before that happens. There's not really any prospect of oxygen levels getting to a problematic level different from where we are now anytime soon. And carbon dioxide, well, if you have too much carbon dioxide, it does become difficult to breathe, but we're a long, long way away from that. The carbon dioxide concentration in the atmosphere is 400 and something parts per million. So no, the danger, we'll get, we'll buy the farm from something completely different long before that ever happens. Well, hopefully we won't buy the farm at all. But this is millions of years in the future if you wanted to worry about that.
Okay, we've got time for just a few more. Pedro, there are a couple questions that are related of methods. I think this is related to geoengineering, perhaps. Talking about how we measure the destruction of ice. Is there any testing being done to slow the ice melting? And someone else asked about if there's something, could we build something like ice walls similar to sea walls to anchor some of the ice in place? So measures being tested like that?
Yeah, there is actually a recent study. I mean, this is all these things, geoengineering, it's fun, right? It's huge. And, we all very creative and we all can come up with ideas. And there is one actually that it was recently, it's been around, that it's building exactly what you said. It's sea walls or sea screens, I think, it's just to try to stop the warm water that is what is melting the ice shelves in Antarctica from underneath. So it's the warm water that comes under in that, a space in that floating ice shelves that I mentioned in that, a sketch that I had for the cross section. And that is the part that is melting them. And so one of the things that are being discussed now, well, do we build huge screens that are floating vertically with buoys on the front of the ice shelves so that warm water cannot get under and therefore melt from underneath and therefore thin? Conceptually, there are tons of things that can be done. realistically, the ocean would destroy or destroys pretty much everything. If you've been out in the ocean on a storm, and you've been in the sea ice on a storm when everyone is breaking up, the strength of nature is incredible. So yeah, probably there are things I can imagine. We're all very creative in many different ways. How many of those are realistic? I think it's in that sense, I would start thinking about, what do we want to do? Is moving the conversation to, instead of that kind of technology that is expensive, risky, and there are many proposals, and we switch into, mitigation. Can we discuss about what can we do as citizens just to try to stop the whole entire process? But yes, there are many proposals out there for doing incredible stuff. I mean, humans, we are very, very creative and inventive.
Okay, I can't fully answer this question, but I will briefly address it. Someone asked what we thought about the movie Don't Look Up. So I'm not sure anyone wants to go on the record as with a movie review, but I would like to say that that movie was almost filmed at Haystack in part, that the famous director came out and had a really great visit, and Colin and I got to see what it's like to watch a Hollywood director get followed around by about 24 underlings who all dressed the same and just followed him everywhere and laughed at all his jokes. It was a great day, but unfortunately it was also right at the beginning of COVID, so we weren't able to make it happen. So personally, that movie is very, very sad for me because it was almost us in the background.
But I like the movie a lot, and it absolutely encapsulated the frustration that scientists feel at not getting the message across. If I may, Nancy, there's another question in here. Assuming you're able to, how do you maintain a sense of personal optimism?
Yeah, I was going to go there next.
Yeah, and I think it's really what Pedro said. We are humans are incredibly creative, and one of the things that we're not good at is making uncreative assumptions that what's been happening in the past is necessarily what's going to happen in the future. So it's true that we have not been able yet to make a significant impact on the behavior of the fossil fuel industry or on the governments that subsidize that. But what we have been doing is innovating like crazy on energy generation technologies. And if you look at the path of photovoltaics, it's become cheaper, far faster, and to a far greater extent than anybody was predicting. And the fraction of renewables is far higher now than the industry projections were just a few years ago. So I think there's plenty of room for optimism that with a combination of things, not with any one thing, not with one government resolution or a Paris Agreement or something else, but with a combination of these things, that we can indeed bend that curve and avoid the more severe consequences going forward.
I think that's actually a really nice question to end on. There's a couple that we haven't gotten to. I want to just briefly, before I turn things back over to Emily, say thank you to everyone. And also, if we didn't answer your question, or if you would like to hear more about what we do at Haystack, I put our website into the chat. And also, when things are a little bit safer and we're further out of the pandemic, we will start having open houses again. So if you go to our website, you can sign up to be informed when we start having open houses. So thanks very much for all the questions. Sorry about the ones we didn't get to, and thanks for all your kind words. And also thanks to our hosts, Emily and Lynn, and Westford Climate Action. So back to Emily.
Thank you. Thank you so much to Dr. Colin Lonsdale, Dr. Pedro Elosegui, Nancy Wolf-Kateri, Heidi Johnson, John Tsai, and Andrew Crowley for this really amazing and informative evening. I also invite you to visit haystack.mit.edu to learn more about the observatory and what they're doing. And I invite you to visit westfordclimateaction.org. If you live in Westford, come and join us. And the rest of you could bring some of our actions and ideas back to your town. We also have a newsletter. Our second edition is coming out next month, and you can sign up for that at the bottom of our Join Us page on our website. Thank you again for attending. I'm glad you don't have to drive home, except it looks like some of you are at the observatory. And think globally and act locally. Thank you so much. Goodbye.
Thank you.
Thank you.
Bye. Thanks, everyone.